guys, welcome to lesson number 4, the logarithmic function. So I'm going to go through this pretty quickly. Please take your time, pause, stop, rewind, whatever you need to do. This is so important that you take your time on this lesson. I'm going to go through it pretty quickly, but you can go through it much slower. So this is what we have to cover today. Review of exponential graph. That's the easy part. We're going to see how it compares to a log graph. We're going to change exponential to log and vice versa, log to exponential, exponential to log. So that's the key today, is to be able to flip back and forth to these two forms. We're going to evaluate logs and we're going to solve problems with logs. So let's start with the graph. All right, if you have y equals 2 to the x, which looks like the first graph that we did in exponential, in that exponential lesson, the very first one. So we have base 2, it looks like this, a few values for x in your table to give you y values of 1/4, 1/2, so we have growth going on here. We have a domain that's real, a range that is greater than 0. We have no x-intercepts, y-intercept of 1, asymptote at x equals 0. So what we're going to realize today, or what I want you to realize, is that a log function is the inverse of the exponential. Now, does everybody remember what inverse means? Well, we studied this a while back, so you might have forgot. Inverse is when you take x and y and you flip them. Well, taking x and y and flipping them would mean that that table of values, all of the ordered pairs are flipped. So if I was to graph 1/4, 1/4 and -2, and 1/2 and -1, and 1 and 0, and 2 and 1, and 4 and 2, I have a graph that looks like this. And that's exactly what a logarithmic function looks like. I hope everybody remembers that a log function, I'll use green for this one. A log function is the inverse of the exponential, and inverse, if you remember back to that lesson on inverses, is always a reflection over the y equals x line, that diagonal line. And look at those two graphs. Definitely a reflection over the diagonal. But what are these characteristics of the log function? Well, you have a domain that's real and a range that's greater than 0. But the log function has y-ER and x is greater than 0. See, these have been switched. The domain becomes the range. The domain becomes the range, and the range becomes the domain, because x and y have been switched. Now let's look at the other characteristics. X-intercept. X-intercept was non-existent on exponential, but x-intercept now is at 1. So we have an x-intercept of 1. Y-intercept, we had a y-intercept of 1 on the exponential. That becomes an x-intercept of 1 on the log function. We have a y-intercept at 1, and now we have no y-intercept. Y-intercept, none. Everything is opposite of what it was, which means this important asymptote at 0, it was at y equals 0, now is at, asymptote is at x equals 0. Okay, I kind of squeezed everything into this first page, but there is the second page in your notes that you can use to fill in this much neater. So if we were to take the table of values and switch all of these values, which is what I just did in the other graph, we would get this. And those characteristics that I squeezed in there You might want to write them down nice and neat and organized on this page. Okay, now something I want you to notice up here. The inverse of y equals 2 to the x. Let's look at the equation for a minute. So exponential was this. Now we said log was the inverse of this. So inverse means you take x and y and flip them. But when we studied inverses, we didn't just flip them, we had to isolate y. Well, we have an exponent now. How do you isolate the exponent? Well, we've never done that before. And mathematicians were stumped when they came to the inverse of exponential. So they decided to introduce a way of isolating the exponent. And that's where logs came from. Log base 2, this example is base 2, of x equals the exponent y. Log base 2, so whatever the base is this small subscript. That's your base. Now y is what we're isolating here. The value that the exponential form used to equal is this number of the log. So let me give you an example. Log, let's start with an exponential. So if I gave you an exponential form of this, well, you know that's true. 3 squared is 9. And I wanted to write this in log form. So I would say log base 3 of 9 equals the exponent 2. So 3 to this exponent equals this number. The 2 is the exponent. What the log represents is the exponent. Okay, don't want to get too far ahead of myself here. Let's go to the next slide. So in general, so this log equation has no base, it's just base c. So here is a base c. Whoops, I'm a little bit off there. Base c of x. It can be written because you have the exponent is the y, the base is the c, what it equals is x. So this is the log in exponential form. Remember when we were doing exponential, there was some restrictions that we talked about. We don't want a base that's negative, and we don't want a base that equals 1. Well, same thing applies here. We don't want a base that's negative. We don't want a base that's equal to 1. And remember the exponential graph? In the exponential graph, we had y was greater than 0. But in the log graph, we have x is greater than 0. That is the domain of the log graph. And that's where this is coming from. X is greater than or equal, sorry, just greater than. There's your log graph. X is greater than 0, not equal to because of the asymptote. There is an asymptote at x equals 0. There's a vertical asymptote. So x is always greater than 0. Okay, let's look at an example here. You have base 2 of x. Y equals log base 2 of x. Now, you can't use your calculator with base 2 because our calculator has a log button, but it is only base 10. But we can use our calculators to evaluate logs other than base 10 by using this change of base rule. So that change of base rule is just useful for our calculators. If we wanted to write log base 2 of x and evaluate it on our calculator, we would have to put in our calculator, so I'm going to write here log base 2 of x. You ignore the subscript and you type in log x over log 2. So this is actually the subscript of the original. And both of these are base 10 because that's what our calculator calculates. Okay, I don't want you to get too concerned about change of base. I am going to show you that in many examples that are coming up. Let's move on. All right, so here's an overview. If we started with y equals c to the x, we're going to get the inverse by switching x and y. So here's the switch of x and y, and we're stuck here because we can't isolate y unless we change to exponential. So the base is c, y is the exponent, y is what we want to isolate, and what the exponential function used to equal is now in this position right here. So c to the power of y equals x. Let's do an example with base 2. So let's write the inverse of this by switching x and y. Now I want to isolate y, so I'm going to write this as log base 2 of x equals our exponent. Let's take some more examples. We're going to start flipping back and forth, and hopefully you'll get the hang of this really quick. All right, here's all of these exponential forms. We want to write them as logs. Log base 3 of 81 equals the exponent 4. Log base 2 of 1 over 32 equals the exponent negative 5. Try the next two. You can pause and try the next two. Hopefully this is what you got. Log base x of 5 equals 2y. The exponent this time is 2y. So this looks a little different, but we're going to treat it exactly the same. The base here is a binomial. So a subscript of 2x plus 4, and a is this position. The exponent is negative 1. You getting the hang of it? Base, exponent, what the exponential equation equaled initially is this position right here. Let's try another example. These ones, given logs, I need you to be able to flip from logs to exponential. Look at this example number 1. No base. No subscript. It just says log 1,000. So you need to know this would be base 10. And hopefully this makes sense, because if we say 10 is the base, 3 is the exponent, we know that 10 cubed is equal to 1,000. So that's true. Let's look at the number 2. Base 5, exponent negative 3, what it equals? And we know that's also true. 5 to the negative 3 is 1 over 125. M equals log base t of b. So this is just to show you that for any letters, variables, if they're in that position, the t is the base, m is the exponent, b is what the exponential form will equal. 4 is a little different because we have a log with a coefficient in front. Before I switch a log to exponential, I have to get it by itself. So I need to divide by 4. So if I divide by 4, now I can switch to exponential. The base is b. The exponent is 5 over 4. And maybe I'll put a bracket around that because the exponent's a fraction. What it equals is 6. All right, let's keep going. Evaluating. So now I don't have any equal signs, but we can evaluate this log. Maybe what we can do here is put this equal to x. That might help us to see that we're looking for the exponent. 4 to the power of x is 64. So I can write them with the same base. I know 64 is 4 to the 3. And the exponent then is 3. Let's look at this one. 2 to the power of something is equal to this. Well, again, I can write 32 as a power of 2. 32 is 2 to the 5. Just checking. And that means that 1 over 2 to the 5 is the same as 2 to the negative 5. So x equals negative 5. X is the exponent. That's what we're looking for. The log expression represents the exponent. Okay, let's do these last two. Try them yourself, and then you can check my work and make sure that we're all matching in our solutions here. No base. That means we're working with base 10. And how are we going to evaluate the exponent here? Well, I think you'll see it a lot easier if we wrote this as 10, 100, 1,000. The third decimal place is the thousandth, so it's 1 over 1,000. A 1,000 is 10 to the 3, so 1 over 10 to the 3 is 10 to the negative 3. So our exponent here is negative 3. Now, all of these calculations wouldn't be necessary for you to show every step. Some of you might have noticed right from the beginning that 3 decimal places is 10 to the negative 3. Okay, look, this one looks a little trickier. Let's make this equal to x so that we know what we're looking for. 3 to the x equals... So you see how closely this is related to the exponential solving that we've done. If you're good at exponential, this is one more step. It's just looking at a log equation and changing it to exponential to solve it. So I would work with base 3 here. Nine is 3 squared. Root 3 is 3 to the 1/2. Now I'm multiplying with the same base, so 2 plus 1/2 is 4 over 2 plus 1 over 2 is 5 over 2. And that's how we would solve for those logs. What else do we have here? Let's check the next slide. Okay, here are some interesting examples. We have a log that is an exponent. What if we solved for this exponent? And what I would ask myself is, what does that log equal? 5 to the power of what is 25? That log represents an exponent. 5 to some exponent equals 25. Well, I know that that exponent is 2. So that log is equivalent to 2. And now I can solve this. Equals 25. Kind of interesting that the answer here is the number that we started with up here. Okay, we'll look at an example similar to that in the next few days as well. Let's do the second one here. X is the unknown. The unknown is the base this time. X to the 3 equals 64. Well, whenever we want to get rid of an exponent, we can do the opposite operation. So cubing, we can cube root. So if we cube root x cubed, we get x. Cube root of 64 is 4. So x equals 4. So you will see solving for the base, solving for any term in the log, not just the exponent. Let's do this one. Base is 3, exponent is negative 4. So this would just be go to your calculator, right? 3 exponent negative 4. And if I go math fraction is 1 over 81. Okay, those examples were just showing you it's not only the exponent that we're looking for in some of these cases. Okay, let's see if you're understanding what this log represents. I want you to pause here and give me an estimate for this log. What would you say this is going to equal? No calculators, just an estimate. What does this log equal? All right, hopefully you have a pretty good idea. What I'm thinking in my head without a calculator is 3 to the power of something is 50. Well, 50 is not a nice power of 3, so I have to estimate. I know that 3 cubed is 27, 3 to the 4 is 81. So that tells me that this log, which represents an exponent, represents an exponent between 3 and 4. Now 50 is close to the middle here. It's pretty close to 3.5. I maybe would say a little less than 3.5, so my estimate is 3.4. Now let's calculate it and see how close that estimate is. Because it's a base 3, I can't enter it in my calculator unless I change the base. So change of base. I type it into my calculator as log 50 divide by log 3. So the 3, the denominator, is the base of the original. So log 50 over log 3 will look like log 50 divided by, oops, let's try that again. Log 50, close the bracket, divided by log 3, and that equals 3.56. So my estimate was a little bit off there, but pretty close. 3.56. All right, so hopefully you're understanding that this is a representation of an exponent. All right, let's do a word problem here. The Richter magnitude. Oh, this is appropriate after the weekend earthquake in Nepal. So that's very hard to watch the news clips of what's happening there right now. Thousands dead in that terrible earthquake. So Richter magnitude. Magnitude of earthquakes are measured in the Richter scale. And it's defined as the amplitude of the ground motion, and that's AO. A is the amplitude of the ground motion, and AO is the amplitude of the actual earthquake. Okay, that sounds kind of confusing, but it's the relationship between those two variables. So A over AO is what we're taking the log of. All right, let's see how that fits in with an example here. In 1946, an earthquake struck Vancouver. It had an amplitude that was 10 to the power of 7.3 times AO. So that's telling us that A is 10 to the power of 7.3 times the original, okay, to the actual earthquake. So AO is the actual earthquake. But look what happens if they tell us that this times this is A, then the AO doesn't even matter. This just cancels out. So what we're looking for, the magnitude is going to be the log, if I write that, the magnitude is equal to the log of 10 to the 7.3. And you see what the base is? The base of this log is 10. So if I wrote that as 10 to the power of m equals 10 to the 7.3, then we know that m is 7.3 because the base is 10 and what it equals is also a base 10. All right, let's look at this example. In 1949, off the coast of BC, the strongest recorded earthquake had a Richter reading of 8.1. So we're going to put an 8.1 in for M. And the question also asks how many times as great as AO was its amplitude. So if we put an M value of 8.1 here, and it's asking how many times as great as this to this, then really we're just asking similar question to what we had up here. We can just cancel out the AOs. We're looking for this value here. So the amplitude is 126 million times. Okay, where does that 126 come from? What we're doing is finding this relationship. So if I actually made this another variable, let's say x, I want to find x, which is how many times great this is over this. And then we rewrote this as base 10. So I'm going to say this is base 10. 10 to the 8.1 equals x. What is 10 to the 8.1? And that's where we get this huge number. And that huge number is 126. Count the number of spaces. If we round it to the nearest millions, is 126 million times 10 to the 8.1. So it's asking you how many times as great, which is asking you for that fraction. What is A over AO? And that's why I substituted in the x. It says compare the amplitudes of the two earthquakes. So we have a magnitude of 8.1 and a magnitude of 7.3. If we're going to compare these, what we're doing is comparing them as base 10. This is 10 to the 8.1. And this original was 10 to the 7.3. When we're comparing magnitudes, we're always looking at base 10. And we would subtract these two. So we have 8.1 minus 7.3. And we get 0.8. So I wouldn't say it's 0.8 times. One is 0.8 times bigger than the other. I would say it's 10 to the 0.8, 10 exponent 0.8, which is 6.3 times. So that was the second earthquake. The 8.1 earthquake was the 1949 earthquake. Was 6.3 times greater. Okay, we will look at examples of magnitude in the homework as well. So we'll get some more practice with this. All right, so hopefully you're getting the idea of logs, and I do want you to do just a couple of quick questions and hand them in to me tomorrow. So this is what I want you to hand in, just on a small piece of paper. You don't need to use or waste a lot of paper because these are very quick, easy questions. Okay, if you wouldn't mind, please doing these 3 questions, writing them on a separate sheet of paper, and giving them to me as you come into class tomorrow. Thank you very much. I will see you soon with lesson 5.